points I took off, that should subtract it from 100. That should be what the front score says. We had 1, 2, 3, 4, 5. We had 5 A's. We had 1, 2, 3, 4, 5, 6 B's. We had no C's. We had 1 D. We had 1 F. Okay? So overall, the class average was an 84. That's good. So good, good. That means the first 2 exams are done, right? We're going to start getting ready for the next one. Make sure my microphone's on, camera. Okay, so we're going to start getting ready for the next test, but that'll be after spring break, right? We have next week and then spring break. Kylie? Right, Kylie? Okay. So I was very pleased with your results, but as you probably could tell, it's pretty much the review, just change things around, right? That's the way it's going to be for the whole semester. So, you know, as long as you stay on track, keep up with the reviews and stuff and your homework, you should be fine. We ready? Yes? Okay, so what are we going to do? We have today, right? And we have 2 days next week, and then we've got our spring break. So my goal is in the next couple of days to get through our next major topic, which is polynomial functions. Were there any questions over the test or anything? No? Okay. Polynomial functions. So what we've done so far, right? So far, we can handle linear functions, f of x. I'm just giving you specific examples, 3x minus 7. We can handle quadratic functions. An example of that would be like something off the test, 2x squared minus 4x plus 7. Both of these, right, you know how to graph these now, right? For quadratic, there was the set of steps. Does it open up or down? What's the vertex, right? Quick sketch. How many X-intercepts do you have, right? You follow the procedure. So now we move into the next group, which are called polynomial. Now, I should state that all the homework for the next 3 days, probably even after spring break, is going to be homework that I put up on the board at the end of class, right? Because really, these problems take a little bit of time, maybe like 20 minutes each to do. So you're not going to have a ton of problems to do for homework. It's going to be a few, but they're going to take you some time, all right? So if for some reason you miss class or something, just go watch the video, go look at the end, you know, we'll watch the whole video, but the homework problems will be at the end. Okay, so our goal now is to come up with a way of graphing polynomial functions. Now, before I do them, I want to just remind you that linear functions were good for modeling certain things in the real world, things that look like straight lines. Quadratics, parabola, remember we were throwing things across, we talked about, it's kind of ironic now that we were talking about how much war influences technology, right? But it does, right? So, okay, so what are polynomial functions good for, right? What are they good for? Well, first let me tell you what they look like, okay? So what do polynomial functions look like? Okay, so I'm going to draw a picture of a polynomial function for you, all right? I'll use a different color. Something that does something like this. Goes up, comes back down, maybe goes up and down and back up again like that. That would be an example of a polynomial function. Let me give you another one. You could go up, you come down, back up, go way down, back up like that. You could do that. And I could keep doing this for the rest of the day, drawing examples of polynomial functions. The thing that they all have in common is that they're smooth, Okay, so they're nice and smooth. There's no jagged edges, there's no breaks in the graph. They're smooth. That's actually a word, a mathematical word. They're smooth and they're what we call continuous. Continuous. That might be a new word for you in a math class. Continuous. What a continuous function is, like the easy way to explain it, is that you can draw your picture, you can draw your graph without picking up your pencil. All right, so you can see for these that I would never need to pick up my pencil to draw this. Also, the arrows at the end imply that the function continues to behave that way for the rest of the graph. So this implies that this just keeps going down and down and down and down and down forever. And then this arrow implies that it goes up and up and up forever. So that's basically what a polynomial function looks like. So it's not as simple as a line in a quadratic, right? A line, pretty simple. Quadratic is either this or that. That's it. There's only two possibilities. Polynomials can wiggle around a bunch. I mean, the number of kind of wiggles in here there's no restriction. It could wiggle 10 times. It could wiggle twice, 3 times. It could wiggle 5,000 times. It really just depends on the function. So where do you think these come up? I mean, does this look like anything in the real world? Does anything that you know of behave like this? What's that? Stock market? Stock market, I mean, if you look at the stock market, it's constantly, up, down. There's trends, it goes up, it comes down, right? That's a common example of a polynomial function, is something like the stock market. If you look at, boy, there's all sorts of things, heart rate, your heartbeat. I mean, you could, now that would be a very uniform polynomial function, something that's, that's more like a sine curve, but you could fit a polynomial onto your heartbeat or something. I mean, there's a lot of places. The thing is, it's not linear, okay? It's not linear, and it's not quadratic, right? Quadratic does just either down and back up or up and back down. Polynomials allow you to have kind of like different changes, right? So that's what they look like in terms of visually. What we're going to be most interested is this, okay? We are going to be most interested in, when we go to graph these, we're going to be trying to find the X-intercepts. See these X-intercepts here? We're going to need to be able to find those. And we're also going to need to know whether or not the left side of the graph goes down or up, and whether or not the right side goes up or down. All polynomial functions, when you look at them on the edges, the left side and the right side, it either has to go up or down. Okay, it's either up or down. It can't flatten out for a polynomial function. So we're going to be looking at what does the left side do, what does the right side do, and then where are the x-intercepts in the middle. That's pretty much the way we're going to attack trying to graph them. So let's look at some examples. These are two specific examples, well, a line and a quadratic. Let me give you some specific examples of polynomials. So here's what they look like. So your first example of a polynomial function is something like this. Let's go x to the fourth minus 7x to the third minus 8x squared. Let's call this example A, okay? That is an example of a polynomial function. It looks a little bit like a quadratic, doesn't it? Doesn't this one kind of look like a quadratic, except that we have x to the fourth instead of x squared? But otherwise, it kind of looks like a quadratic, yeah? Okay, let me give you another example. How about this? F of x equals negative x to the fifth plus 9 x to the third. There's another example. I'm going to keep going. I'm going to give you one more. How about this? F of x equals, let's go x to the sixth minus 3x to the fifth plus 4x to the fourth. Sorry, make that a minus. Minus. And then plus 12x to the third. These are just three examples of polynomial functions. So let's discuss what they have in common. Like, what makes a polynomial function a polynomial function? Well, poly means many, right? Many. And then I have many nomials. That's what it is. Many nomials. A nomial is basically a term. A term is something separated by addition and subtraction. So can you all see here on this first one, I have 1, 2, 3 terms, right? I have 3 terms. This second one, I have 2 terms. And this last one, I've got 4, right? So a polynomial is basically a bunch of terms, added and subtracted together. How many there are, there is no limitation. You could have 1,000 terms, okay? You could have, doesn't matter. We are going to stick to just like 2, 3, or 4. I won't give you anything more than that in this class. But generally speaking, we can have as many as we want. The other thing is that all polynomials, if you look at the powers on the x's, look at all these powers, right? 5, 3, 6, 5, 4, 3. All the powers are positive integers, okay? All powers on a polynomial must be, well, first of all, these are all positive numbers, right? And an integer is like a counting number. 1, 2, 3, 4, 5. No fractions. You can't have fractions, you can't have decimals, all right? That's what you need in order to have a polynomial. With me? So all polynomials is just a bunch of terms where the powers must be positive integers. Okay? If you have that, you have a polynomial, right? That's what you have. Now, when you look at a polynomial function, if you look at each of these, you're going to have a highest power of x, right? Each one of these is going to have a highest power. This one up here has the 4th power is the highest power, right? This one, the 5th power is the highest power, and this one is the 6th. Sometimes the order, when it's written down, is not in this order, like highest power down. Sometimes they'll try and trick you and they'll stick a x to the 8th back here or something. The highest power of x that you see is called the degree of the polynomial. Okay, so this right here is the degree of this polynomial. This is the degree of the polynomial. And this is the degree of this one. Oops, degree. All right, so you would call this like a degree 4 polynomial, or a 4th degree polynomial. This is a 5th degree polynomial. This is a 6th degree polynomial. And out of curiosity, I'm thinking back now, hold on. I said that a linear function that we studied already, I gave you an example to start out, right? And I gave you, I forgot, was it 3x minus 7?
Yes.
Yeah, 3x minus 7. Okay, and then the quadratic, I gave you an example, and I said it was 2x squared. Tell me if I'm wrong here. Whatever, it doesn't matter. I gave you an example of one of each, right? Okay? Are these polynomials? Yes. Yes, these are actually polynomials. This has 3 terms, but more importantly, this is a degree 2 polynomial, right? And this is a degree 1 polynomial. A degree 1 polynomial and a degree 2 polynomial. So what I'm telling you is that if you think about polynomials as being like this big set of functions, right? There's a bunch of polynomials in here. Within this big group, there's a smaller group, which are your lines, okay, which are all of these. And then there's a group in there, which are all your quadratics. But there's more than just lines and quadratics. There's a bunch of other stuff in here, and that's all these guys. Make sense? Okay. Now, we have the degree. The next thing we need to be able to recognize, and I'll explain to you why it's so important that you understand what the degree is. Would you all agree that finding the degree is not that hard? We're just looking for the highest number, right? That's not that difficult. The next thing I want to point out for all of these is that once you find the degree, you have the x, there's always going to be a number in front of that. In this case, it would be a 1, right? In this case, it would be -1, and in this case, it would be also a 1. This marker's done. Oh, that table's in my way. Let me see. I'm going to try and bank it in. Up. Oh, okay. Here, let's see if this one works. Right, 1, 1, 1, right? That number is called the leading coefficient. Leading coefficient. Now, I don't like to write leading coefficient over and over and over, so I'm going to from now on just call it LC, okay? LC stands for the leading coefficient. So for all the examples I gave you here, well, not for all of them, but for this one, the leading coefficient is 1, the degree is 4. Leading coefficient -1, degree is 5. Leading coefficient is 1, degree is 6. Now, why is that important? Why is that important to be able to know the degree and the leading coefficient? Well, do you remember when I drew the pictures, I said that the left side has to go up or down, right? And the right side has to go up or down for all polynomials? We can tell what it does by just knowing these two things. And what it takes for us to actually come to some conclusion is something called the leading coefficient test, which I'm about to give you. Okay, so here we go. The leading coefficient test. How to determine the left end and right end behavior of a polynomial function. Okay, how to determine the left and right hand behavior of a polynomial. This is, so I'm saying, how do we actually determine if the left side goes up or down, the right side goes up or down? We use the leading coefficient test. Which, again, I don't want to have to write that over and over and over. So I'm going to call this LCT from now on. And here's what the leading coefficient test says. It's actually, it doesn't say anything. I'm going to just let me put something up here, and then hopefully you'll make sense out of it. I'm going to draw a table. Okay. Like this. Almost looks like a tic-tac-toe thing. What I'm going to put here is degree even, degree odd, LC positive, LC negative. Now, you know, I gave you a reference sheet for this past test, right? I gave you a reference sheet, and I think it probably helped some of you. This is something that I would recommend you have for the next test's reference sheet, what I'm about to put in here. So first, let me explain how this table is going to work. Remember, if I give you a polynomial function, it's going to be easy for us to find the degree and leading coefficient. We're just going to visually get them, right? Once we look at them, we're just going to see where we are in this chart. So first thing we want to look at is whether or not the degree we have is even or odd, okay? So like, let's look at the first one there for A. The degree is even, right? So I know I'm working in this row. And then what I do is to figure out which of these two it is, I look at whether or not the leading coefficient is positive or negative. And in this case, the leading coefficient is positive, right? Because 1 is a positive number. Make sense? So degree even, leading coefficient positive means that this is where I'm looking, right? Now, let me tell you what happens, all right? If your degree is even and your leading coefficient is positive, here's what the polynomial will look like. The left side must go up, the right side must go up. And in the middle, we're going to put a question mark because In the middle, it might like do a bunch of wavy stuff, but I can tell you that the two ends are going to go up no matter what, okay? Now, if we have a degree that's even and a leading coefficient that's negative, all that happens is this gets flipped over. So you go down on the left, in the middle we don't know, and down on the right. Make sense how this chart's going to work? Now, if you have an odd degree in a positive leading coefficient, your left side will go up, your right side will go down, and then over here on this one, it's the opposite. Left side down, right side up. So for all polynomials, you're either this, this, that, or that, right? That's what's happening on the edges. This, that, or that. That's it. And you can just easily determine that from the leading coefficient. So let's go back over here, and let's just look at these, and let's just, underneath them, we'll say what they're doing. This one was a degree 4, which is even. The leading coefficient was positive. So we know that this one should go up, right? Up, up. Pretty good, huh? Pretty impressive. I've been out of the classroom too long. I used to be 98%. Up, up, right? How about this one? Who wants to tell me what this one does?
Down, down.
Down, down. What's the degree?
5.
5. Is that even or odd?
Even.
Careful.
Oh, okay.
Remember, think, what are the even numbers? 2, 4, 6, 8, 10, 12, right? Odds, 1, 3, 5, 7, 9, 11, right? So odd would mean we're down on the bottom row, right? And then leading coefficient is negative, isn't it? So we would be this one. Down on the left, up on the right. Are there any questions? Raymond, that makes sense?
Yes.
Okay. What about C? Up, up. It's just like the first one, isn't it? Even, positive. Even, positive. So up, up. Okay, now the question mark is the big challenge here, all right? We know what the end behavior is. This test allows us to find the left and right end behavior easily without doing any work, really, just looking at whether or not a number is even or odd or positive or negative, right? That's it. The hard part is to figure out the middle, all right? So let's talk about how you find the middle. To find the question mark, do y'all know what I mean? Like in here, to find out what that middle piece is, you find the X-Intercepts. Okay, you find the X-Intercepts. And how do we find X-Intercepts for a function? Set it equal to 0. So to find the X-Intercepts means we will have to take the function and set it equal to 0. That's what we'll have to do. Okay? So now that we've got the basic idea of what we're going to do, let's try just without, I haven't given you any formal steps yet. I am going to give you like step 1, step 2, step 3, just like we did with the quadratics. I will give you that. But let's just see if we can do the first one, if we can sketch it with just what we know right now. Okay? So if I asked you to sketch the function f of x equals x to the 4th minus 7x cubed minus 8x squared, right? Then the first thing I know, right? I could say, well, first thing I know is that the left side goes up. I don't know the middle, but the right side also goes up, right? We've already done that, right? This was basically us using the leading coefficient test. Now let me try and find the x-intercepts. That'll be my second thing I'm going to do. Let's find the x-intercepts. So we have to take this function and set it equal to 0, right? Ooh, okay. Well, if this was a quadratic, right? If this was quadratic, I wouldn't be that intimidated because I would always have the quadratic formula, wouldn't I? But this is not a quadratic. So what we're going to have to be able to do, and this is where things get a little bumpy for people, is we're going to have to be able to factor here, okay? You're going to have to be able to factor. And I'm not, now in terms of like the level of factoring I expect from you, I don't expect like super high level factoring. I just expect that you can factor a GCF, greatest common factor, and that you can do factoring of difference of squares, and that you can do factoring of trinomial. We've done all of them at some point in here. So let's see how this goes. First thing I'm going to do here, looking at the left, is try and pull a GCF out, greatest common factor. So what do all of these terms have in common? They all have at least one x, right? Do they all have at least 2? Do they all have 3? No, but they all have 2, right? So I can pull 2 factors of x out. So I'm going to write that like this, x squared. And then I have to write a set of parentheses equals 0. And now inside here is what's left after you pull an x squared from here, here, and here. So what happens when I take 2 of these x's away? What am I left with? X squared. Okay, what's left here when I take away 2 x's? Minus 7x, right? And then if I take 2 x's away here, minus 8. That good? What's in parentheses, now that's something that you can try and factor because this is now a quadratic, isn't it? And we can play that game that we played before, right? If you were trying to solve this before, factor it. Do you remember this thing where we did the number in front here and multiplied back here? And we got negative 8. And then we looked at the number in the middle, negative 7. Try and come up with 2 numbers that multiply to be this and add to be this, right? What are the numbers? What are they? Negative 8 and positive 1. You multiply those, you get negative 8. You add them, you get negative 7. So that means that this would break down to be, see, we put minus 8 here, plus 1 here, you put the x here, you put the x here, and then remember that thing you had to leave a space out here for the number in front? But here it's a 1, so I put 1 here and underneath doesn't change anything. So that's my factored form. Now look, you have to be able to factor, okay? This right here you have to be able to do. I know with quadratic functions, when we were trying to find the x-intercepts, you kind of got saved because you could use the quadratic formula. With polynomials, you have to be able to factor this. Something like that, you have to be able to do this, all right? I'm sorry, but you have to. You'll see why in a minute, all right? Questions on this? Okay, so I'm going to rewrite this. This becomes x squared. Then I have x minus 8. And then I have x plus 1 equals 0. So once I get to this point, we're at a critical stage right now because we have now completely factored this. And just like we did back when we were doing quadratics, we have this equal to 0. We set each of the factors equal to 0. So I'm going to set each one of these to 0. X squared equals 0. X minus 8 equals 0. X plus 1 equals 0. And I'm going to solve each one. Okay, why don't you solve those real quick? I'm going to jot these down over here because we're going to do these problems next. So I need some board space here. What's the solution to the first one? X squared equals 0. What's your solution? What number squared gives you 0? What's the only number you can square and get 0? 0 itself, right? So your only solution here is x equals 0. And then here? Well, it was negative 8, right? It was minus 8, so you have to add 8 on both sides. So x is positive 8. And then here, negative 1. Okay. Are we good? All right, so right now, I know what the end behavior is, right? And I know where this graph hits the x-axis. Would you agree? Any question? No?
I'm just listening, sorry.
Okay. I'm going to try and graph it, and you're going to see when I do this, we're going to run into a problem, all right? So here's the way I'm going to graph this. Here's my x and y axis. First thing I'm going to do is I'm going to plot my x-intercepts. I'm just going to put these on the x-axis as dots. So let's see, I need negative 1, 0, 8. So let's just say this is negative 1 right here. This right here would be 0. And then 1, 2, 3, 4, 5, 6, 7, 8. There's 8. I have an x-intercept here. Now, these are the only 3 points that your polynomial can cross or even touch the x-axis, right? We should have no x-intercepts anywhere else. Those are the only ones, okay? Y'all agree? Because we solved the equation. We also know that the left side goes up and the right side goes up. So since I know the left side goes up, that means that from this point moving to the left, I have to go up, right? Why can't I come down and then back up? Why couldn't this come down and then go back up over here? What would happen? It would cross right there, wouldn't it? Wouldn't I cross the x-axis? And then I would have created another x-intercept that I don't have. And remember, polynomials are smooth and continuous, so it's not like you could come down here and then just jump up there with your pen. It all has to connect together. So it can't possibly do that, right? It has to do this. Okay? And then you could say the same thing on this point. To the right, it's got to go up, right? So I know that my graph looks something like this. Okay? So far, that's what we know. Not bad. Not bad. What we don't know is what happens in the middle. Okay? What we don't know is what happens, other than that I have these x-intercepts. So let me show you a couple of things that could happen and why we're not done here. That there's more work we have to do. Do y'all agree it could do this? That looks smooth and continuous, doesn't it? That's one thing I could have done. But that's not the only thing I could have done. I could do this also. I could have had it come down like this, kind of bounce off that point and come through here and then connect like that. That could have done that, right? What else could I have done? I could have done, well, I could have done this. I could have bounced off there and bounced off there and bounced off like that. It could have done that. Do y'all see there's all these different variations of what could have happened?